Hey, good morning, chemistry students. Today we're going to be finishing up pretty well, just two more concepts left for our organic chemistry chapter. And the topic today is going to be condensation reactions, which is carrying on our study of esterification reactions that I presented last time. Okay, so condensation reactions are very important in biology. It's mostly how all your proteins and many different polymers in your body are made. Okay, and they always start from carboxylic acid. So we're carrying on our study of carboxylic acids and the reactions of carboxylic acids. Okay, so our biology students would have seen this in probably chapter 2, I think, in the biology unit, in the biochemistry unit, and discussing how proteins are made. Okay, so in your body you have amino acids. Here's an amino functional group. Here's your carboxylic acid functional group, and you have around 20 amino acids in your body, and then your body will then use condensation reactions to make combinations of those amino acids to make functional proteins, all right? And in that condensation reaction, you'll have the carboxylic acid group of one amino acid being joined to the amino functionality of another amino acid through a condensation reaction. They join together, they spit out this molecule of water, and they make what's called a peptide bond. That NC double bond O is a special type of peptide bond. And peptides are pretty strong. We don't dissolve in water in our swimming pool, for example. So this water can't really go back in there that easily, all right? In your body specifically uses, like if I took glycine and another glycine molecule and I just heated them up, they're probably not going to react. You need catalysts. Like for example, in the Fischer esterification reaction, we needed an acid catalyst. So in your body tends to use enzymes, okay? And the biology students know which enzymes in the ribosomes, how we make the polypeptides, okay? All right, so on the other hand, your stomach is a highly acidic environment, right? And there's a lot of water around, so we can push the equilibrium back to the starting materials in the presence of acid and a lot of water. So your body will break down these peptide bonds to release the amino acids by reversing the reaction and putting water back in. Okay, so that happens in your stomach. It says right here, your stomach digests proteins by reversing the condensation reactions by adding water back into the molecules. And that process is called hydrolysis. Okay, so we have condensation in the formation of these bonds and hydrolysis in the breaking of those bonds. They're both related. Okay, so the relationship between condensation and hydrolysis, just to give it a good picture for that. Okay. In the esterification reaction, like I showed last time, you have an alcohol, like ethanol, reacting with a carboxylic acid to remove water. That's a condensation reaction. It happens in the presence of concentrated sulfuric acid. Okay, and then if I'm not careful and I have a lot of water kicking around, the reverse reaction is going to happen. Okay, so there you can see these double arrows. That's an equilibrium. So you have the condensation reaction making your ester, but if I have a lot of water kicking around, and I increase the concentration of water, I can make the reaction go back. So if I did this reaction and I never removed water or actually had a lot of water around in the reaction would never happen. Okay, you're pushing the reaction back to the reactants. So in order to form esters, we have to try to dry them out. We have to remove the water from it as it's been made. Okay, so esters can be formed in nature as chemicals are drying on rocks, okay, because the water would be released. All right, and that's kind of how, when people are talking about how interesting polypeptides were made in the primordial soup or the formation of interesting molecules on Earth, they imagine the Earth was really hot and these types of chemicals are floating around in a sea. And as chemicals are drying on rocks with a lot of heat, condensation reactions happen to make some interesting proteins that might have some functionality to do enzymatic work. Okay. Now, one thing we didn't talk about, and I'm just going to try to speed up the rest of this unit so we can get into the option. I'm not going to cover everything in this unit, but one thing we didn't talk about for the higher levels is naming esters. SL students didn't need to know that, okay? So if you look on the back of a fragrance bottle or back of your shampoo, you'll find there's a lot of esters in there. Esters are responsible for flavor and scent, usually. Okay, and what you would see is the name looks something like this: ethyl ethanoate, or methyl methanoate, or methyl propionate. Okay, and what is that ethyl responsible? And what's that ethane responsible for? So if I look at the ester link, okay, the molecule that came from the carboxylic acid. Okay, so if I look at this, I'd say that part came from the carboxylic acid, or more likely that part came from the carboxylic acid. Ethanoic acid in the reaction. So that part is listed here, okay? That part is over here. So I have 2 carbons, so that's ethane, okay? Ethane O8. O8 represents an ester instead of oic, which is acid. So ethanoate is that part. And ethyl is the part that's attached to that oxygen over here. So if this was 3 carbons, that would be propyl ethanoate. If it was 1 carbon, that would be methyl ethanoate, okay? If this was 3 carbons, that would be ethyl propionate, okay? And so on and so on, okay? Just for you to have an understanding of where that goes. So just to repeat, the O8 part is the ester. That just signifies there's an ester in the molecule. Ethane O8 signifies that there's 2 carbons attached to the carboxylic acid that made the ester. And ethyl is whatever's attached to that oxygen through an ether linkage, okay? All right, so how are condensation reactions used in technology? So other than biology, we actually use condensation reactions to make all the nasty plastics that are floating around a craw, okay? So condensation reactions have been really important in technology to make plastic type polymers. And I'm going to present to you a few different polymers that we make out of them. So many polymer materials are made from condensation reactions. And what you need to find is you need to find some special molecules that can react with themselves many times, okay? So for example, in this molecule, I have a dicarboxylic acid. I have 2 arms, this carboxylic acid and that carboxylic acid. Okay, this can react with an amine to make a peptide bond. All right, that's not an ester, this would be a peptide bond. Okay, but then I'm left with another carboxylic acid, another amine on the other side, and they can just keep going back and forth. An amine can come in here, and they can make a long chain, a polypeptide chain. So as long as I have 2 handles for reactions on these molecules, they will then react upon themselves infinitely, forever. Okay, and what you end up making is a polyamide linkage. You can see that here is the part of the molecule that came from the dicarboxylic acid molecule that I put in the reaction. And here is the diamine, and they just keep reacting. On this side would be another dicarboxylic acid over here. On this side would be another diamine, and they just kind of go boink, 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 back and forth, back and forth. And the molecule that we first discovered to do that is nylon. Nylon's an important material that we use in clothing, okay, and fabric. And we would have probably done this reaction in class if we had the lab still open, because it's a really fun reaction to do. And I'm just going to show you what it looks like, okay? So both these, the dicarboxylic acid and a diamine, they're liquids, and they don't mix. So if you take a look over here, one of the liquids is on the bottom, the other liquid is on the top. They don't mix together. And at that interface, the reaction starts to happen. So if you take a look at the video here on the right, as long as I take a piece of paper or something and I dip into the bottom layer and start pulling up, the reaction starts to form. And what I can end up doing is I'll extrude a fiber of nylon. Okay, that's like making a thread of nylon from the reaction. It just comes, like oozes out, comes out. And you can see this person here is winding that. The faster I wind it, the thinner that fiber is going to be. So this person's winding that fiber on a glass rod. And the reaction is happening in real time, being pulled out. And it's happening at that interface. That's pretty cool. So I can play around with what's attached over here on my diamine to change the properties of the nylon. Okay, make it tougher, make it looser. And then we can have a whole variety of nylon polymers for use in many things. Okay, Kevlar. I wonder if you took a look at what Kevlar is. What kind of a polymer is Kevlar? Right, that's the bulletproof polymer. Okay, then another type of polymer that we use, polyesters. Those are also fibers for sewing and thread and artificial materials. Okay, and polyesters are made just by having a carboxylic acid and an alcohol within the molecule, and then that molecule is going to polymerize on itself by forming an ester. This carboxylic acid is going to react with the alcohol of another group, okay, and they'll react head to tail to make a really cool polymer. Okay, so lots of different polyesters are in your clothing. If you look on the back of your shirt, you'd see that your shirts are not 100% cotton. They contain polyester threads, and they're extruded in a very similar fashion like that. As the reaction's happening, you can pull the polymer out of it. Okay, so here's a task. Draw the repeat unit for the polyester form below. What molecule is lost? Okay, this is an activated carboxylic acid. Okay, if I took a carboxylic acid and I reacted it with chlorine, you make this molecule, that carbon is going to be extremely positively charged, meaning that it's going to find anything that's negative to react with. The lone pairs on the oxygen are going to want to come in. All right, so you can just imagine that that is just a really fancy carboxylic acid that wants to react. All right, and you can see that these are the dicarboxylic acids, that's the dialcohol. All right, when they react, this is going to go head to tail. This is going to go to another one of those, and we make a polymer that looks like that. And then molecule you're going to be releasing, instead of water, you're going to be releasing H and Cl. So you're going to be releasing HCl gas from that reaction. Okay, but this reaction would happen a lot faster. This is more likely what people do in a real lab just to make the reaction happen faster and be a more efficient process. Okay. All right, and then here's just another example of a reaction to make Dacron polymers, okay? So this also looks like a carboxylic acid, but it's protected. It's an ester form of that carboxylic acid. If I put an ester in the presence of water and base, okay, metal oxide, if I put it in the presence of water and base, what's going to happen is that ester is going to break apart and form the carboxylic acid, okay? And then that carboxylic acid will react with the alcohol, as I showed, to make the ester, and you'll make a polymer. That's Dacron polymer. All right. Last thing I just wanted to review, and we're going to play some games in class, is an organic chemist has all these reactions in mind. And so whenever we look at a molecule, we know that, hey, that's an ester. I can make an ester from a Fischer esterification reaction, which involves reacting an alcohol with a carboxylic acid. So we can start to look at the structure of a molecule and break it apart and say, what was the building block that built that? That's a dicarboxylic acid, that's the alcohol. And we'll be able to design a way of synthesizing a molecule that we could find in nature. So organic chemists use reaction pathways. Now this is just like, I would say 2% of all the reactions that we know as organic chemists, okay? But these are the most basic reactions that you would learn in your first year organic chemistry course, probably your first semester at university. You would be taking an organic chemistry class, and you'd have to have these reactions memorized so that you can then take a look at a molecule and apply it, okay? So just going through what we did, we started with alkanes. I taught you guys how to make halogen alkanes, and then we talked about that as a functional group. With halogen alkanes, I can then do elimination reactions to make an alkene in the presence of base, okay? In the presence of base, I can also make alcohols, all right, from the halogen alkanes, all right? And then from the alkenes, I can then go backwards and I can make an alkane by hydrogenation. I can make the halogen alkane by adding these mineral acids. I can make alcohols from alkenes using water and sulfuric acid catalyst. I can make dihalogenal alkanes by adding chlorine, bromine, and iodine. And I can just polymerize the alkenes to make plastic polymers. Okay, and then from the alcohols, we learned that we can make interesting functional groups from that by oxidation, ketones, aldehydes, carboxylic acids, and then the reaction between carboxylic acids and alcohols gave us esters. So all those I showed you. So we can play around, I can draw molecules, and I can say what would be the building blocks, or I can give you reactions with things missing, like these guys, and you have to tell me what it is. And that's basically what your organic chemistry class is. It's playing Lego with molecules and becoming an alchemist, memorizing reaction conditions. And the most fun thing was when they took us into the lab and we had to make antibiotics from scratch, or we had to make materials from scratch. That really opened my eyes at my first year university, and I thought that was the most fun thing ever. All right, thanks.